also seeing nowadays, and this is more or less due to the big data explosion, if you like, is that people are trying to give interpretation to latent models, like factor analysis and so on, using big data, using variables that you know very well, as opposed to try to be in front of your latent variables and then think, what could this resemble to? You try to use this automatically. So this paper, for instance, is using convex optimization to do that. And we are using, again, MinLP, mixed integer nonlinear optimization. Okay, at the end, I will show you some pictures, some visualizations, so that when you are going to fall to sleep, you can wake up with nice colors, yeah? Good. So my aim is that I cover at least 2 of the bullet points, yeah? And then maybe we go for a break, yeah? And then we come back. Is that okay? Yep. I'm the boss today, yeah? This afternoon, yeah? So I can decide when I go, right? Okay, nearest neighbors. Yeah, I told you that I was going to talk about nearest neighbors, yeah? So nearest neighbor is having a multi-class setting. So my multiple classes here are with different symbols, yeah, in the visualization. And then what we do is that we try to identify prototypes of these classes. So you can see that I'm pointing there at some of the observation in such a way that if I was going to do nearest neighbor classification, I forget about the whole data set and I only remain with my prototypes. Yeah? So that selection of prototypes, so to choose your best prototypes, is what we decided to do in one of the papers some time ago. So as I said, the classification, when I'm trying to classify this observation, when I try to classify this observation, then I will look only at the prototypes and not at the rest. Not aiming today that you follow me in all my formulations. You will have the slides, you can study them, but at least I would like you to appreciate that sometimes I will have discrete and linear models. Sometimes I will have discrete and nonlinear models, and sometimes I will have nonlinear models simply, yeah? So, and then what my aim is to tell you where is the technology from the point of view of optimization. Where is the technology? Is it, fully advanced, or is it just dealing with the small problems? Yeah. So this is what I would like to show today. For instance, in this case, the technology is out there. This is a mixed integer linear problem, no issues. Yeah. It could be that, they take a little bit more time than a linear problem, but they are okay to be solved. So what we did here, it was to choose our prototypes, in such a way that my misclassification error was as small as possible. So this is my misclassification error over here. So I have a class, and my prediction doesn't coincide with a class. That's an error, and then I try to sum up across the whole training set. I have to choose my prototypes, so I have to choose K prototypes, and I have to then, every time that I make classification, I have to find my closest prototype. So I do with this type of constraints, yeah? So nice, because it's only, I'm only having 0, 1 variables in the training set. Even these assignment variables, I can show that I can relax them, which is a great thing, yeah? So we did this some time ago. This is actually pretty new work that we are doing as of now. And you may wonder why I'm talking about trees if I told you that my trees are very, very, very interpretable. Yeah, so that will come in a second. So what is a tree doing? A tree is basically having your whole training set over here, and it's going to go splitting your training data set all the time, a little bit more and a little bit more. And what you are trying to get is more and more purity on your children nodes. What is purity? Well, you are assuming that you have, in this case, you have good payers and bad payers, yeah? Yeah, so for instance, in a credit score sample, at the beginning, you have the whole training data set at the top. That's an impure node, but if I split it, if I was very, very lucky, the bad pages will go to one node and the good pages will go to the other node, and then I will end there. It's not going to happen, but in principle, that's what you are aiming all the time, improve your purity. So normally your nodes are going to be defined by simple hyperplanes of your predictor variables. And I say simple hyperplanes because here you only have one variable playing a role. So this is what we call orthogonal cuts, you know, where you only have one predictor variable playing a role. Now these trees, for a long time, they have been built heuristically. More than that, totally greedy. You know, they only look locally whether age and 50 in combination was the best cut to improve purity. Now, we don't know what's going to be happening lower in the tree, but at that point, it was the best cut. So you were maximizing your purity locally there. Now, there are colleagues that decided that, you know, very recently, so colleagues in IBM, colleagues in MIT, and then we too, that decided that we could be optimizing these trees. So instead of deciding locally what is the best to do, you try to make a decision for the whole tree in one go. The whole tree. So for every single node, you have to decide whether you take age as a predictor and whether you take 50, but you do that for all the nodes in one go. And of course, what is going to be your objective function? Your objective function is going to be, again, your error, misclassification error, right? And then you have to choose your variables, yeah? We can do that with 0, 1 variables, yeah? And we have to choose your cutoff. We can do that with continuous variables, so it's not a problem. We can do that. It was a problem 30 or 40 years ago because we didn't have the technology there. Yeah, we couldn't do mixed integer linear programming as well as we do nowadays. Now, you would say why our work is different from the one that it's out there in the literature, and this is something that we have done actually in several papers. And we have learned, you know, that this is not a bad thing to do. When I told you before that the tree was taking age and the tree was taking 50, one always wonders, you know, 50? Why 50 and not why 50.5 or 51? You know, a random number. Why does it need to be a hard 55 if it could be a soft 55? So that's what we did in this paper, and we have done this in another paper. In machine learning, we have to be a little bit more, you know, aware of the uncertainty that you have in your data, and it's much better to take soft decision rules than hard decision rules. So how did we do our soft decision rules? So imagine, I think you are going to recognize this function. Yeah, so this is the logistic function, right? And what we did, it was, instead of saying, you know, that you have a 50 here, and then saying that these ones are classified as negative and these ones are classified as positive, we use this logistic function to tell you what is the probability to be classified negative and what is the probability to be classified positive. Yeah, so there are two advantages to us. So one of the advantages is that we really treat better the data. Yeah, because the data is not black and white. The second advantage to us is that we remove some of the integer decisions that the other papers have. So we can actually, work on a continuous mode with, I should admit, a highly nonlinear objective function. So let me show you that. Okay. Now, remember that I was talking about before about age above 50 or age below 50. So I have here a hyperplane that defines the cat at each of the nodes. So at each of the nodes, I'm going to have a hyperplane. It's not going to be age, but it's going to be something a little bit more complex. It's going to be a combination of all my predictor variables, yeah? And the coefficient that I have on those predictor variables are these a's, yeah? Now, it's a hyperplane, so therefore I'm going to have an independent term, mu, yeah? And I'm going to also have, for every terminal node, I have to decide which class I will be assigning to that node, yeah? So remember that you will have a tree like I drawn before. So here in this terminal node, I should know whether this is a positive node or a negative node. And these are now decision variables. But also the hyperplane that is defining the cat. So you have these decision variables. So for every terminal node, you have to decide one of these classes. So you make a decision whether it's positive or negative. And actually, your feasible region is wonderful. If you ever had a very, very simple course on operations research, you would have heard about the total unimodularity property. This feasible region has the total unimodularity property. So actually, in principle, these variables used to be 0, 1s, but I can relax them because of the total unimodularity property. So very, very friendly feasible region. Awful objective function, because I have to calculate, every single observation, yeah, what is the probability of ending here? Because I have a soft way of taking decisions. So if I have a soft way of taking decision, it's not a black and white. Every single observation will end up in every single node, but with a different probability, right? And then I have my misclassification error, the usual one, yeah? So it's this probability that makes my life a little bit hard. Now, look at this. We are very, very happy to actually, in a very simple way, making this hyperplane sparser. So we have local sparsity by only penalizing the L1 norm of the coefficients of the hyperplane. Yeah, very, very simple way. Any single tree that you find in Python, in R, or whatever, is not able to control how many predictor variables you are using because it's greedy. But we have a very, very simple way of controlling ourselves. And this one, by using the norm infinitive, then we are controlling how many predictor variables you are using across the whole tree. Not only locally, but also across the whole tree. So that if you are able to use as few as possible across the whole tree, then it's nicer in terms of, the cost that you have for gathering these predictor variables. So for this one, we have done, actually, we are redoing to satisfy the needs of the referees, which normally tend to be quite a lot. We are revising these results, but anyway, they give you more or less an idea of what we have been able to achieve. So these are data sets that are standard in the literature. You may like them, you may not like them, but we have to use them because this is how we can test with other papers. Yeah. So and I can show you that they vary in terms of the amount of features that you have, predictor variables. They also vary in terms of the classes that you have and how imbalanced they are, as well as the size in terms of the data set. Okay. I love these slides, so I'm hoping that I can make you visualize them. Now, we have talked at the very, very beginning that trees are very easy to interpret. When we run in these data sets the trees, some of them went up to depth 18. So depth 18, it's a quite difficult rule to understand. If, and you continue with another if, and you continue with another if 18 times. Yeah? So that's not, yeah, they are easy to interpret if they are short. In our case, we made them short, but of course at the cost of being, you know, a hyperplane. Yeah? So meaning that you can have the many of the variable places are all. Yeah, but this is depth 1. So actually you only have 2 terminal nodes. So what we figure out is if you look at the red, is your accuracy. Yeah, your accuracy can stay for a long time the same. So accuracy is good as high as you can. Yeah, can stay for a long time the same, while your sparsity is improving and improving and improving a lot. So this is what we can see in this here. So actually your tree is using less and less explanatory variables in both senses, in sense of the local sparsity and the global sparsity, but you have the accuracy flat. Now, the running time that we have here is a few seconds, while the papers that we talked to you about using integer optimization, they were running for several minutes and getting less good results than we did. We also did it for depth 2. Obviously, you can improve your accuracy with depth 2, and then still you see the same pattern as before. Yeah. Okay, I do a little bit of support vector machine, and then we go for a break. This is basically the tool that we wrote a survey on in 2013. So actually, what I'm going to show to you is some of the work that we did a little bit later, but it has already a couple of years old. So in support vector machine, what we are doing is trying to again use hyperplanes to build a classification rule. So here you have an example in which things are quite easy. So you know, the good people, the bad people, they are clearly separable. Yeah. And so in support vector machine, you have the option of the black, you have the option of the pink, and actually you go for the pink because what you want is to be your hyperplane to be as far as possible from your data. Actually, I always visualize support vector machine as a very thick pen going through the data. The thicker the pen is, the better the support vector machine is going to generalize, because there is more margin between the two classes. So there is this concept of margin, which is the distance between the two classes. Yeah, and the hyperplane of SVM is really at the middle of that margin. So it's all about separating hyperplanes. Yeah, so it's plenty of geometry here in supervector machine. Now, this is the classic formulation of supervector machine, in which what you try to do is separate the two classes. So here you have, so you would have, in this case, if you were going to do just this, then you will have perfect classification. Because you will have here that this is a positive guy, and then to get this greater than or equal than 1, then you will also need a positive guy. Then you have a negative guy, but you need something bigger or equal than 1, then you will have you will need a negative prediction. Yeah. So if you impose this, then you know that the two classes are separable. You in life know that the two classes in general are not separable, and this is why you add this term over here, which is a deviation. So this deviation allows you to have, some misclassified objects, but then you try to penalize that misclassification over here, together with your margin, which I told you that the larger your margin is, the better. And you may say you are minimizing, you are not making, yeah? But actually the margin is related to 1 divided the norm of your normal vector. So this is why the maximizing the margin turns out to be something to do with the minimization of the Euclidean norm of this vector. Yeah. Now, this is a model that by now we know how to solve very well, we and the community. It's a quadratic convex model with linear constraints. This is very friendly. It's not linear, but actually when it's convex quadratic, these non-linearities, they don't harm us. They are quite easy to handle. Yeah. And if you like, there are quite some of my colleagues in optimization that they got, trapped, by this model, and they are working on it still. What we did was more about, how can I make this model a little bit more visual? Perhaps not for you, because you are very used to working with hyperplanes. Yeah, so for you that would not be an issue. But this model, for someone who doesn't engage with any quants, this model is just much more visual than a hyperplane. Yeah, the hyperplane is always challengeable because the coefficients that you have in front of them, people will try to give an interpretation to these coefficients. People would try to say, what is the meaning of this 3.5 in front of h? So we decided to go into that direction, simplify these coefficients. I don't know whether I will be evaluated in this summer school, but I'm evaluated in my MBA programs, in my MSc programs, yeah, when I teach, right? And some of them say that they strongly agree with the quality of the teacher, and some of them would say that they strongly disagree with the quality of the teacher, right? So how do we call that? That's a Likert scale, yeah? So that's what we did. We did the following. You have H. Instead of saying, that you have a hyperplane in which you have 3.5 multiplying H plus other things, we limit the amount of values that you can put here. In the simplest case, you can go you agree, you disagree, you are neutral, yeah? In a more sophisticated case, you would like to put something here in the middle, or more and more and more, yeah? So this is what we call a Likert scale. Of 3 points, but we also did a Likert scale of 5 points or more points. We did more. We did more. So what we decided was not to say in advance that it could be -1, 0, or 1, but to decide what number you want to put here. And we took the opposite there. So we gave more flexibility when building, yeah? When building this value here, but it's still limited to a discrete amount of values. So instead of writing there -1 or 1, we wrote A and we wrote A. And the A had to be decided by us. Now, the beautiful thing is that we never let the user see the A. We only let the user see whether there is a strong agreement or a strong disagreement, or whether that variable doesn't play a role because it decided to go to the 0, the coefficient. Yeah? So this is one way in which I will visualize the classifier in a second. Another thing that we discovered is actually we could profit again from sparsity. So we were trying to be more visual, but we could also be more sparse. And that actually makes sense. Because before, your coefficient could be any number, 3.5, 375, whatever. But now, if you were too close to 0, when you allow only a discrete amount of values, you are trying to be attracted sometimes to the 0 because your coefficient wasn't so big in any case. So it was better to basically, converge to the 0. Yeah. So I will try to visualize this with you. Anyway, look at this. Independently of what I'm doing, it can be, I mean, the next formulation, you are not going to like it, so enjoy this one, yeah? So what I'm doing is actually, constraining the amount of values that my coefficient can have to a discrete set A, yeah? It's just I need to put this into the optimization package, so to do that, I have to do a little bit more work, yeah? But that's what I'm doing. So this is what I just shown to you, so I could have a 3 Likert scale representation of the coefficient, or I could have a 5 point Likert scale. And this is the way my SVM with this discreteness is going to look like, because now for every variable, I have to see whether I will take that discrete value, yes or no. That's what I'm doing there. As simple as that. It doesn't look so pretty. It's because I had to delete some absolute values that I have and so on, but it's as simple as that. There is a decision variable, a 0-1 decision variable that you have to make. Yeah? For every single predictor variable that you have to know at what value you are going to end up and whether it will be the positive or the negative. Yeah? Now, the nice thing is that we figure out is that actually if this A becomes a parameter to tune, then this objective function is not quadratic anymore. It's actually linear. And that's what we did. And for one of the data sets that you have seen before, and apologies for not showing you the entire set of predictor variables, that's what we did. For every predictor variable, we are showing you, whether the variable was agreeing with being a good customer or not. So agreeing would be when the coefficient that you saw in the variable was pointing towards the positive class. Yeah, so the positive. And this green is when it was pointing towards the negative. So you can see that, well, I'm not showing you the whole data set, but you can see that 4 out of the 10 variables that I have here, they end up having a 0 as a coefficient, so they were not playing a role. So the sparsity that I was talking about. So as I said, the user doesn't see the value A. As long as you can with the value A, then they will try to give an interpretation to that value A, but we remove that from the picture. Now, when we were running the accuracy of these methods, we saw that actually the accuracy was the same, yeah? Not exactly the same, but, you know, in less than 1 percentage point distance, you know, from the one that the SVM would have. So actually, we don't lose accuracy, and we gain this interpretability I was talking about. We also did it with more points, but then your sparsity reduces, obviously, because in the infinite, if you have an infinite amount of points in your Likert scale, is the same as having a continuous representation of your coefficient. Let me show you one quickly, and then we go for the coffee break. This is something that we are working a lot at the moment, not only for super vector machine, but also for other tools like logistic regression and like also in trees. Categorical variables. So I showed you at the beginning of my presentation, I showed you this data set about procurement. And I told you that the language could be Polish, Spanish, Danish, English, etc., etc. That's a typical categorical variable. Yeah. The way that we put categorical variables into machine learning, when it comes to this type of separation hyperplanes, is that we put a 0, 1 variable for each of the categories of that. Now, not really a good idea in many ways. Nowadays, we record more and more big data. Yeah? So we know more about our customers. So we are increasing the amount of categories for one single categorical variable. So we are actually making it harder for ourselves to interpret the coefficients of these categorical variables. Yeah? Because in my data set for procurement, I have 30 dummies for language. So I would need to interpret 30 dummies to understand whether the language plays a role or not. But actually, the only thing that I want to know is whether language is important to the model or not. How do I translate these 30 coefficients into language being relevant or not? Second thing, there is a structure there of my 30 dummy variables being linked because they belong to the same, there is a hierarchy. They belong to the same categorical variable. They belong to language. But once you have modeled them as dummy, you lose that structure. And I can tell you that there are more complex structures, you know, to categorical data that you are missing if you just do these dummies. So what did we do here? We did clustering. Now, and we are doing this at the moment with my procurement data set too. So you have your 30 countries. My 30 dummies for the variable country. So what about constructing 2 clusters for these countries so that you don't lose accuracy? I don't want to lose accuracy. That's my main goal in my whole presentation and in my whole life. Yeah? I don't want to lose accuracy. So I'm going to try to find the best clusters towards accuracy. So I'm going to try to build these clusters inside my method at the same time that I'm building my classifier. I don't want to do anything in advance because that's not well connected. So now you will see me doing clustering inside the supervector machine. Guess what? We figure out that we don't lose accuracy and then we gain a big plus. became a big plus. Because now what I'm doing is, I have now cluster 1 of countries, and I have cluster 2 of countries, and this is just simply one dummy variable. Yeah, I only have 2 categories now, 2 hyper categories, if you like. And now I only have 1 single variable, which is, if you like, I could call it new country or something like that, new variable country. And now I only have 1 coefficient to interpret. So life is much easier if somebody would say to me, do I think that country plays a role in this, lack of competition? I will look at my hyper, variable that I have created, and I will look at whether the coefficient is significant or not, and I take that decision. Yeah, but the most important thing is that you will see me building my clusters inside the classifier.
Is it something that
you are great. Yeah, now you know. Yeah, that I get questions.
So is it something that you can say in general that you don't lose accuracy by using only 2 clusters, or is it like?
I'm afraid that although I'm a math person, I'm afraid that I cannot prove. I cannot give you a proof.
So you would have to test in every case for every data set separately.
I'm afraid that our work in machine learning ends up being empirical. Yeah. So yeah, fair point. Maybe you are not that great anymore. No. That's a criticism about But you can see that actually the theoretical works in which you try to prove whatever consistency, statistical consistency or not, the machine learning has such a beautiful structure that is not the one that that they will give you in general a good accuracy. So so it's these 2 worlds that you have to put together. I'm just telling you my experience. I will not oversell it. So my experience over this year is. And it makes sense because you have so much, so many possibilities in making those clusters. Yeah. So, and as I said, I'm not making them in advance thinking about north of Europe, great but bad weather, south of Europe, less competition but better weather. I'm not making these statements. I'm just letting all the possibilities run. Good. So, by the way, I was trying to say 2 clusters, but I could build more. So eventually you get there. But of course, for me, 2 is the ideal point because then I have only 1 single coefficient to interpret. Yeah.
Otherwise, you just reduce the number of categories.
You are trying to reduce. Yeah. You don't want to have the 30 numbers to interpret. And actually, some of the statisticians that will tell you that they have ways of building them. I'm just telling you that I built them. I let the classifier decide them. So hopefully you can visualize this. It's easier. I go back to the formulation. Yeah, it's actually one of the most unfriendly that we got in this PhD. So this student was doing a PhD on supervector machine, and this is one of the worst that we got. Okay, so this is actually the same data set that you saw before. Yeah, this one that was a little bit shortened. Yeah, so it's a credit score data set, and then you have categorical 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Yeah, I was not daring to say 11, but that was my recollection. You have 11 categorical variables, and then you see this continuous line telling you, the categories for each of these categorical variables. Yeah, and then what we did, it was to create the clusters, and some of the categorical variables have a lighter color and some have a darker color. So the lighter color will go together into one basket, and the darker color will go together into another basket. And then what you do is try to decide your coefficient for your cluster. You don't have any more all your categories. You just have cluster of the categories, and then you will take a decision about what coefficient to assign to that cluster L. So in our case, it was 2 coefficients that we needed because all our experiments we did it with 2. Now, this is where life is a little bit harder for us in optimization. So I have to tell you, I'm an observation. Yeah, I'm an observation, and I have a predictor variable, and I have to decide to which cluster I'm going. So these are 0, 1 variables. Yeah, 0, 1 variables. Yeah, but they will need to be multiplied by a continuous variable, which is the coefficient that I would like in that cluster. So the multiplication of these continuous times a 0, 1 collection of variables, this is a semi-continuous constraint. On the top of that semi-continuous constraint, you have okay, it's still friendly, it's still quadratic, convex, but we have a feasible region that is not so friendly. So what we did here is, beginning of our test, we decided, this is a min LP, yeah, mixed integer nonlinear program optimization. We gave it to the solver. No way. So here what we did, it was to build a lot of heuristics to try to deal with the difficulty of the problem. So what I'm saying is that when it comes to min LP, small problems and non-linearities, you have to, not everything is still, a technology there, but that's nice because I still have a few years to retire, so I can continue writing papers, okay? So now you really deserve a coffee break.
Yeah, but the nonlinearity is the product of binary and continuous, right? That's it. That's the source of nonlinearity.
And we rewrote it with Fortet.
Yeah, but by McCormick or whatever, we can.
We rewrote it, but then the problem becomes it enlarges, right?
But it's MILP at the end. It's mixed integer linear program at the end.
Sorry?
But at the end, it will not be nonlinear. It will be linear at the end, right?
No, you still have 0, 1 variables to take.
Yeah, but it's linear. Yeah, it's mixed integer, but linear. It means that there is no nonlinear term anymore.
It's quadratic.
I mean, it's quadratic.
Yeah.
Okay, it's mixed integer quadratic.
No, by rewriting, that's what we did. So we gave several ways of rewriting them, and for all of them, we did try to solve the relaxation and then build a heuristic space on the relaxation. But yeah. So. Okay, guys. So I think I have until 4 o'clock. I think. So let me go back to these slides. Sorry, I'm perhaps compressing quite a bit of information in my slides. But some of your colleagues made some comments, so I thought, yes, we did rewrite this, using Fortet, but what I was trying to say is that this formulation is not very strong. And I think I was trying to explain to some of your colleagues that it makes sense that, by the way, the formulation is not very strong because you have a lot of variability in the way you can build these clusters, right? So the information that you have in these relaxed 0-1 variables is not very rich, especially if you have big M constraints like you have in that case. Good. So what I'm going to show you, this is actually something that we just got out in March. It's some work that I'm doing with one of my colleagues in CBS, in Copenhagen Business School, together with a PhD student from Seville, my hometown, So I will do some publicity at the end, I love to be in Denmark, but you can't beat the most beautiful city in the world, So anyway, so benchmarking models. this is exactly what I'm trying to sell nowadays to people. So we have done for many years, optimization to help machine learning. We have done machine learning to help optimization. I didn't show today, but there are people, doing that. There are people who are trying to, tune branch and bound methods using machine learning, etc., etc. But the thing is that what we would like is that this machine learning is helping us to take decisions. So actually the machine learning has to be integrated with the decision-making model that you are using. So this is just a very, very simple example. And I hope you can appreciate that if my decision-making model is based on optimization, and I am doing data science based on optimization, it's very easy to merge them, because they are written in the same language, this math language. So that's what I'm going to do here. And I apologize, I cannot start, very basic explaining, but okay, you probably get the idea of benchmarking, right? So I am using some inputs to generate some outputs, and if I were using less inputs, I'm producing more outputs, that would be excellent, but normally life is not so simple. Normally I will be using more inputs, less inputs than another person, and I will be producing more output, less output. So if I want to do benchmarking, I have to work with a linear combination of these inputs and these outputs. Apologies, I'm having a hard time with the pointers. It's my fault. So what I'm having here today is I'm going to show you a classical model. It's very old, Charnes and Cooper, 60s, many of you weren't born, Me neither, by the way, So I'm having K-firms, and I'm trying to see which ones are efficient, which ones are inefficient. And when I talk about efficiency, I talk about a linear combination of my inputs, relative to a linear combination of my outputs, and that linear combination is optimized. It's optimized so that I can see who are in the Pareto frontier and who are outside the Pareto frontier. So that has been, a classic model that we teach in operations research books. It's actually a fractional optimization problem, but when we teach it to the students, we say to them, okay, this fractional optimization model actually can be rewritten as a linear programming model. So I cannot credit myself here at all, because the one who knows a lot about benchmarking is the colleague I was talking about. And one of the places in which he helps basically the European Union is in the benchmarking. Look at me, I can do electricity, in the benchmarking of DSO's operators, So there are two schools of thought, So there are the statisticians that will build for you a stochastic frontier analysis model, and there are the optimizers that will build for you a data envelopment analysis model. So these two schools. So I'm going to go for the lower school, but actually with my colleague, we are trying to merge the two schools through, again, data science. So in the classic model, what you have is for each of the firms, you are trying to calculate the efficiency of the firm, and the efficiency is going to be bounded between 0 and 1. And then what you do is a weighted average of the outputs and a weighted average of the inputs. And the model decides the weights so that it discovers which are efficient with respect to the other ones. And the thing is that my colleague was doing this for a while. He had to basically build, define a model. And to build the final model, he was using different features, yeah, different inputs, different outputs, yeah. But he was running through all these possibilities himself, and so the literature does, yeah. So people are using a priori rules, in advance, information theory rules in advance, or even exposed, they will eliminate some of the inputs and some of the outputs based on, the coefficients or based on the domain knowledge or whatever. So what I said to him, why don't we try to incorporate the two of them into the same model? And that's what we are going to do. So I'm going to show you how to select your inputs and your outputs in a joint manner. So let me show you the model. Okay, so, and here is where you have to be with me in terms of what is the original model and what is that we have added. In the original model, what you have is that you are trying to maximize the efficiency. I told you that the efficiency is a number divided by another number. But actually, we know, yeah, from modeling tricks, if you like, in optimization, is that a fraction can be rewritten in this way, yeah? If we know something about the denominator not being 0 and the denominator not changing sign, etc., which is the case. Now, here is this denominator that we are talking about, so it's normalized to 1. So this is the one in which you are imposing something about your fraction, and this is where we come. So we decided to do the feature selection using 0, 1 variables, yeah? And then this will end up being, your big N constraint, because if you don't choose this output, then you know that the coefficient has to be 0, and you need a big N constraint there. We did it with the outputs, but we can do it with the outputs and the inputs. Now, this is if the model, if you like, for only one single individual, but actually, what you would like to do this is for all the individuals. So for all the individuals, you need one single model. And one single model that we will use to measure who is efficient and who is inefficient. So we can do this by basically building now a model in which your objective function is the average of all your efficiency. So we are actually accommodating our model to say the average of our efficiencies. In a second, I will show you that we can do it for other objective functions. So this model is a little bit larger than before, because now I don't have only one individual, but I have everybody here. So I have everybody here. But the decision of the inputs and the outputs is the same for everybody. Yeah, so it's a decision that does not depend on the firms, that is general for everybody. So, and the objective function is going to be maximizing the average efficiency. Now, because we are having a optimization point of view, you can accommodate other objective functions. So instead of looking at, on average, what is our efficiency, you could look at, giving weights, if you like, but also look at how far you are from efficiency. Yeah, so how far you are from efficiency, and then trying to optimize that. Or you could also try to look at the worst and try to maximize that. So a max mean point of view. Or even you would like to optimize a percentile. So you would like, that 75% of your firms are as high as possible. Yeah. So in general, I get mixed integer non-linear, formulations, because I have the 0, 1 decision variables, but I also have some non-linearities like here, or some non-linearities like there in the min-max. With this formulation, I'm not going to present all of them, but one by one, I can tell you that we have addressed them in the paper. So, and let me pick up on a couple of those that I love. Sometimes you have two features in your model that are highly correlated, and if you don't do anything, they would like to be in the final model. Because if one of them really likes to be in the final model and is highly correlated with the other one, the final model is also pulling that one, right? If you have a sparse model, you basically pull out one of them because you are kind of giving a budget of how many variables you want in your final model. What some people have done, and we have done that too, is that you put into the model, constraints that forbid to have highly correlated variables into the model. So it's a simple, if constraint that is very easy to model, but basically that makes much cleaner your model. Yeah. And unfortunately, we have read quite a few papers in benchmarking in which the variables that you end up having in the model are highly correlated, which doesn't make sense if you are trying to build a very, very selective model. Another thing that we have extended our model with, and this is something that is done a lot in policy. So when you are trying to benchmark, for instance, in the case of electricity markets, they realize that the regions in the country are making these companies to function in a very different way. And the example is in Brazil. And then in Brazil, my colleague has been working together with them to build two different models for the region. Yeah? So what about detecting the regions yourself? So what about detecting what is that, clusters, again, the firms into two groups so that you can give them more flexibility with benchmarking, So now you don't benchmark to the whole group, but you benchmark to your closest group, yeah?
Pass this.
Sorry.
I'm gonna throw it again. Where are you?
So you show whether you're a good basketball player.
Sorry, which of the constraints, so how are you guarding against corner solutions?
About corner solutions?
Is it the denominator constraint, or the sum of all the alphas?
You mean that I don't...
So that you get like big clusters in one...
I see. No. You are, yeah, good point about this. So, I wish I would have brought the slides on this model. We started again thinking, we let entirely the model decide the groups. At the stage that we are now, is at the stage of helping a little bit the model to decide the groups. And when I show a couple of slides more, I get back to your question. So what is that puts together, what is that, what's the way of finding a kind of a group of firms that they like to agree on something? So it's a bit of game theory. It's a bit that I'm going to show you now, yeah? So, but I come back to that comment. So you see me here having this word strategic is because I'm going to show you, I don't know do game theory, I'm not overclaiming myself, but we have started to work into that direction. So, and you will see in a second. Anyway, it's the first time I tell you, actually, I should have said, what software I'm using at every point, but anyway. So this is a data set that my colleague has worked in the past. So it's 182 DSOs. We have simplified ourselves, but we could have taken the whole data set. We have simplified to having 100 outputs and one input, but that doesn't matter. I mean, we can run everything on the whole data set. is that he advised that these were the most important to basically work with. And we normalize the data. This is very usual in machine learning. I don't know. I'm hoping that you can visualize what I'm doing. But what we did is to give a few seconds to the optimizer. Yeah. So to solve the model that you saw, to select P outputs. So we did for P equal to 1, so we selected only one output. We did it for P equal to 2, we selected 2 outputs, and so on, and so on, and so on, until 10, yeah? And then we were, also showing what the selected features are. And in some sense, this agrees a little bit, not entirely, but this agrees a little bit with one paper from colleagues actually back in Spain that have worked a lot in these benchmarking models, so Jesus Pastor. And then this agrees a little bit with the idea that these models are concatenated, yeah? So if you know what are the good features and you want to add one more, that's what you do. You take the good features from before and you try to search for the next one. It's not entirely true all the time, yeah, but it ends up being true later on. So you can see that actually our average efficiency obviously increases because we are giving the model more flexibility. So at the beginning, it's actually a lot of the companies look bad because the average efficiency is 55. And at the end, already with 10 outputs, the average efficiency is 87. So, meaning, this is the most important part for my colleague. My colleague basically needs to extract what are the very, very, very relevant features. So what he was trying to do is do this in advance. If you would end up doing this in advance, you again lose, the information that your benchmarking model is giving you about efficiency. So we try to integrate this into the model. Also, what we gave him, it was the possibility of generating these features using different objective functions. So trying to see whether these set of features were very different if you would use a different objective function. Now, here you visualize the efficiencies, and you can see that actually the slope is going down. Yeah, although you cannot prove the concavity because you have the 0, 1 variables, but in general is flattening, meaning that you already with them are very, very much at the plateau, and then therefore you don't need to keep increasing your model. You could have selected the 100 features, but then you have to again be interpreting these 100 features as opposed to interpreting 10 of them. Now this goes back to your question. We were very, very curious how every of the firms will visualize this joint model. So, and what do I mean by visualize? Okay, so let me say that we are 100 in total, yeah? So we have built a model in which we select the features that satisfy all of us together. But as you know, satisfying everybody together, that doesn't exist, right? Because, maybe I prefer, a certain temperature when I go to my office, but my roommate will prefer another temperature, and we try to be in the middle, but that's satisfying nobody. Okay, so let me build my preferred model. I have my preferred model in which my efficiency looks the best, so in which I select P features, but really selfish to me. So that's what we did. How many models do we have up to now? 101, because I told you that we had 100, liar. 183. I told you that we were 182 companies, yeah? And then there was one more model, which was the joint model. Is that okay? So everybody has a model, and then you have the joint model. And then what we did is what they call cross-efficiency. So what efficiency do I get with one individual model And what efficiency do I get with the joint model? Right? Are you still following me? More or less. It's a nice answer, more or less. And then I see whether I prefer a individual model or the joint model. So that's the cross efficiency. And then I don't know whether you can visualize this very well, but these bars are telling you how many people were preferring an individual model to the joint. How many people were preferring the joint model versus an individual model. And it turns out that if you increase the number of features, these histograms moves toward, preferring the joint model. So with more features, the joint model is able to capture, more the characteristics of all these companies. Yeah. So what did we do? Now in our new paper. In our new paper, we say, okay, who would you like to follow? Would you like to follow the joint model, or would you like to follow her model or his model? Yeah. So we try to talk about followers, and then in that way we do a kind of a k-means idea of constructing the cluster by iterating through all this process. So you have the joint model, and some of the people would like to follow that model, but some of the people would really prefer something else, and then we try to construct with that information. Yeah. And in that sense, what we have seen up to now is that we, as you said, we don't end up having, an empty cluster. Of course, I could have said that I want every cluster to have so many people, but we have not added that constraint yet. We are trying to see whether we get these balanced solutions that you were mentioning. Okay. I think it's time now for pictures. Yeah? In every picture, behind every picture, there is a whole mathematical model. Actually, all these pictures belong, I have to give credit to a great, great, great PhD student that we had. So now he's in Carlos III. So Carlos III is one of the universities back in Madrid, yeah? And I hope you can appreciate, again, some of the MinRP models that we had, yeah? Okay. Now, remember that you already kind of saw this matrix, yeah? So I'm going to be showing you visualization of data, and the visualization of data will be about how much related we are, yeah? But also about, a matrix about me, yeah? So think about one example that I will give you later. Think about regions of a country, and think about adjacency of these regions, yeah? So I will be showing you the Netherlands, and I will be showing you population rates, and I will be showing you basically adjacency of these regions, yeah? So that's what I'm trying to represent. I'm trying to represent these things as accurate as possible, but also these things are as accurate as possible. So, okay, so this is the first paper that we wrote. So this came out in math programming last year. So this model is about, as I said, you are trying to visualize all these objects, but you don't put a dot there, but you have to put, say, a circle. You've seen it before? So this is the center of the circle, and this is the whole circle, and it has to end up being on your screen. So omega is your screen, yeah? And, well, I would like to optimize, that not everything comes in the corner of the screen. So it has to be spread out in my screen. But I would also like to make sure that the relationships that we have, they are well represented there in the visualization map. If you ever did some dimensionality reduction techniques, you have heard about multidimensional scaling. And if you did ever multidimensional scaling, this is an object version of multidimensional scaling. Normally, multidimensional scaling is placing dots. We are placing objects. So this is why they liked it, the paper, because we can do some convex optimization over here. So this is an example that is classic in multidimensional scaling. These are financial markets, and we are trying to represent the correlations between the markets, yeah? And we are also trying to represent the size of the markets, yeah? So what we did, it was to basically do global optimization over here in this problem. So we have constraints in the case of a circle that are quite easy to model, and also in the case of a square or a rectangle. And we have an objective function that it's that's the main issue in our case, that has some distance, some norms, and then we have to do their global optimization techniques. So we did here the representation of the financial markets, and you are not going to guess what this is. Yeah? Do you like music? So this is data on musicians, yeah, and this is the Rolling Stones, and the blue ones are the ones that have been influenced by the Rolling Stones, and the yellow ones are the ones that were influenced that influenced the Rolling Stones. Yeah. Okay, continue. Yeah, you like this, yeah. Okay, I do more. This is the paper on the news data. Yeah, I've shown you that we did some visualization of news data. So I showed you the topic of immigration, and I showed you circles, yeah? But now what I'm doing is rectangles. So you probably heard about word clouds, yeah? So word clouds tend to be rectangles, and you can make the rectangle larger if the word is more important, or you can make the rectangle smaller if the word is less important, and then you can turn the rectangle to use better your space, yeah? So again, we are optimizing here something about accurate representation of the relationships, spread, and something about the overlapping. So, okay, is it going to work? Yes. Okay. So you can see that this is the topic that I showed you before, immigration, and we are letting it go from, was it 95? Up to 2015, I believe. And you can see Norebro there, you can see Aarhus, you can see some politicians that may not be familiar to you, but to the Danish they would be. You can see some political parties like the F, yeah? Actually, you can even see a politician, I did my PhD in the Netherlands, so a politician that was killed, and they thought that it was something to do with an immigrant. It turned out that it wasn't, and you can see him over here appearing. Yeah. So what we did to build this dynamic visualization is that when we were placing the rectangles in one period, we were trying to make sure that the next period the rectangle wouldn't be moved too much from that place. Yeah. And this is something that we have done it in clustering also. We try to make sure that there are not many movements from one period to another period when you do modeling, so that the trend, you discover the trend, basically. Anyway, one more. So this in which I have to turn around the rectangles, I have to make a decision whether they will be landscape or they will be a portrait, but I could also have more options, and they are over here. Yeah. So this is a min-LP that we solve. Now this is slightly different. This model is about making a visualization, but the visualization has to use the whole screen. So I show you the visualization, and then we go back here. So believe it or not, this is Little Netherlands, yeah? So 12 provinces, and you are trying to visualize there the population rates of the 12 provinces. So that would be South Holland, yeah? And you have here North Holland. They are next to each other, and they appear in the visualization next to each other. Actually, that's what we do in our model. We try to visualize as well as we can the portions, but we are also trying to visualize as well as we can the adjacencies. So there is a trade-off, and actually there is in graph theory, there is an incompatibility result in which you cannot represent accurately both, your adjacency and and the size of your portions. So it ends up being a trade-off, and that's what we do. So if we try to represent very accurately the portions, then you will miss some of the adjacencies. So this is what we did. And apologies for this. It's a little bit of a long formulation, but what you are trying to do is we had a grid, and then for each of the cells in the grid, we were trying to decide to which of the provinces of the Netherlands would belong to. And then we are trying to represent as accurate as possible the areas. And then you have to make sure that you measure correctly your adjacencies, and there are many auxiliary variables to do that. And this is for the people who asked me before about Fortet. Yes, we do Fortet in many papers, including this one, as you can see. And finally, yeah, this one. So here we are visualizing, instead of using rectangular portions, what we do is that we use what we call box-connected portions, yeah? So if a cell is over here and if another cell is over there, we need to make sure that there is an L joining them, yeah? So this is the connectivity, and in this case what we are trying to represent is the Morse alphabet and the confusions that you have when you transmit a letter using the English alphabet. Okay, so for me, I live with optimization, so everything I say is going to look beautiful, yeah? So, but I truly believe that through visualizing, data science through a math model, it will help you to integrate with the other models that you are using in energy, me in benchmarking, other people in other areas. Yeah. So what we are doing at the moment, as I said, is that we are working quite a bit on the quantification of categorical data, and we continue as usual working on the visualization of black models. I just wanted to do a little bit of promotion. Yeah. Just 1 second. It's because you may want to check out. We are going to be, for 4 years, organizing a lot of events that have to do with data science and with optimization, including a Neuro Summer School next year in the most beautiful city of the world. July 10th to July 19th. So if you follow us either in Twitter or on our website, we will be, it's not only limited to these people, yeah? These people are just contributing to the field to organize many events. So these people are, some of them universities, some of them industry, and we went through a long process of applying, to the Horizon 2020 to do exchange between academia and industry. So actually, it's we are quite enjoying and going in July to a geospatial, a company specialized in geospatial data, and I've been already traveling to some of the companies, and some of our students are doing the same. It was short publicity, yeah, and yeah. I hope this slides will help you to maybe find something new in your life. If not, I really appreciate that you have been here looking like if you are, engaged. Okay. Any questions?
Sorry. If this can work like that, so maybe I need some help.
So two questions. So the first, if there are solution methods for improving interpretability also for regression models. The second for neural networks.
Yeah, and I promise you to address the second one, and I have to apologize for not having addressed the second one. I was a little bit worried about the time. Regression ones, yes, it's something I didn't mention here, but what I basically, every time that I've been talking about supervector machine, you could have also done supervector regression in a similar idea, and then everything that we have developed today, you could be doing that. There are also some colleagues that basically are working on best subset method, so basically selecting the best features for regression. And I would say that if we talk later, I can give you some references. So yes, there are. Yeah. Neural networks. Yeah. I love to, when people ask about that. The interpretability of neural networks, I'm sorry because I'm losing my voice, it's low. It's low. I mean, the fact that you build all these layers and then you compound, information of your features is low. So it's something that we are tackling. We are planning to tackle. Some people would say that they have addressed interpretability, but what it ends up being is trying to do, again, sparsity. But if you compound, the sparsity is not helping you enough. So it's, again, I can give you some references, but it's not, I would personally say to you that it hasn't been tackled well yet. More questions?
Is the code for some of the models, especially for the decision trees and the SVMs, is that like something that's available somehow?
We have not been so aware that it was a necessity to do that. The papers to come, that's what we are planning to do. I mean, you can always write to me, and then I would say, okay, my student will provide the code, but it's not a code that we have in GitHub or anything available. Yeah, it hasn't been a necessity before, but now we realize that, we should be doing that.
Some of the people that are not like very oriented to machine learning, they say that, for example, some of these methods squeeze the data with intricate models till they get something that may be artificial, not like real. Do you think maybe the interpretability and the paths that you're taking with your team are actually trying to address that fact that we're not just like using data to get patterns even if they are not real?
And for this, I would tell you that I'm in an economics department, not being an economist. And this is the first place in which, they are quite reluctant to machine learning as the final method. What you see now the economy is doing, which again I love, because it tells me the same story as my benchmarking paper to you, is don't let machine build your final model. Let machine learning help you to basically select things, and that's what they are doing. They have models with many parameters, and they let machine learning help them at the very beginning, and then they go ahead with their econometrics models. That's where basically the very innovative, I would say, part of economics is now at the moment. So same with benchmarking. I wouldn't like to be responsible for building the final benchmarking model to be, assessing DSOs in Europe, but I would be very happy to help them to basically iterate through as many models as I can with the knowledge that I have, so that they don't need to do this in a very ad hoc way, if you like. Does it devalue my life? Well, maybe because I'm approaching the 50s, I don't mind. But I don't think it devalues my life. It says, that, there have been so many mistakes about machine learning models, and they all make the jokes in these big presentations about big data, the father finding out about the pregnant daughter and so on. I don't make those jokes because I don't want to overclaim my models. My models will help iterate through many models, more models than, than the people are doing at the moment.
Okay, any more questions? Okay, let's thank Dolores again. Thank you so much for